Okay, so we are getting into what's called Taylor polynomials. And what this is used for is to approximate a value. So, like, the sine of 30 degrees or the sine of pi over 6, we're able to use the unit circle. Some of you might know the hand trick. You're able just to figure out what it is, okay? And it's, you know, sine of 30 would be 1/2, okay? Well, what do you do when you have like sine of 75? Well, you could actually do 30 plus 45 to get 75 because those are on the unit circle. And that's what I'm doing with my pre-calc kids right now. But what do you do when you want to know the sine of 0.1 or the sine of anything else? Okay, you can use a Taylor polynomial to approximate. It's a polynomial, so that means it has many terms, and you could probably assume that the more terms that the polynomial has, what will happen? The more accurate the answer is. Just like anything else we do. Like when we do Riemann sum, the more blocks we have in there, the more accurate the answer is. Okay, so this will show you, this applet, that the more just, exactly what you said. If you have two terms, here's the actual sine wave, the black wave. And then if you have two terms, that's the purple part. So it's getting close to that function, but obviously like not super accurate. Just more looks like a cubic function. If we increase the amount of the terms, so if I have more pieces in my polynomial, closer, it just keeps getting closer. So once I have a decent amount of pieces, I can actually get that wave. So we're going to be doing approximations. With that comes error, so we're going to be calculating some error eventually. But literally all you have to know how to do is take a derivative to come up with the Taylor polynomial. And you're also going to be dealing with factorials once again. Okay, so that's what we are doing today. So everyone should have those notes. And the formula for calculating a Taylor polynomial looks way more complicated than what it is. This is like that textbook formula. But you're going to have two values. You're going to have where the function is centered, and that's going to be my C value that you're seeing in multiple places. And then you're going to be actually evaluating or approximating for a certain value. If I'm trying to evaluate for the sine of 0.1, which I'm actually going to do here in a second, then I'll plug the 0.1 in for x. So C is where the function is centered, and that whole concept of the function being centered is going to actually be what we're doing next week with intervals of convergence. And then the x is what you're actually trying to calculate. What this formula is saying is that you just do f of whatever that number is. So you're going to be given some sort of a C value. You just do f of that. Okay, that's easy. I just plug that number in. Then I multiply it by the first derivative, and I'm adding that to the multiplication of the first derivative times the x minus the center. There's a pattern because this keeps going on and on. You add every time, but you do the second derivative times the piece centered squared over 2 factorial. You do the third derivative cubed 3 factorial. Fourth derivative to the fourth over 4 factorial. So we don't see a factorial here because it's actually 1 factorial, which is just 1. Okay, but if it helps you to think about that, whatever derivative you take, if I'm taking the first derivative, that means I'm going to have this piece to the first over 1 factorial. If I'm doing the second, everything is 2's. It's not like I've got some 2's and then some 3's and then 4's. It's really easy to remember. It's actually easier to just remember it than to try to use this formula, like look at the formula and try to figure it out, okay? Once you get in the swing of things. There's something called a Maclaurin polynomial. It is literally the exact same thing as a Taylor polynomial. It just means that it's centered at 0, okay? So you'll just be plugging in zeros everywhere you see a C, okay? And there's really no need to write x minus 0. You could just write x. But if you want to write x minus 0, that's fine. So on the AP test, if it says something about a Maclaurin polynomial, you need to know that it's centered at 0, because they're not going to tell you that, okay? You could very well be given a Taylor polynomial question, and maybe it just tells you that you're centered at 0. It doesn't matter. It's the same thing, okay? It's kind of like how a square is also a rhombus, that kind of deal. So a Taylor polynomial, a Maclaurin polynomial is a Taylor polynomial. It's the same thing. It's just a specific case where it's centered at 0. So we are going to use those formulas to do some approximations. And whenever you're approximating, when your answer is not exact, you always want to use that little squiggle equal sign. So for number 1, what we are going to do is we're going to find the Maclaurin polynomial, which right off the bat, that tells me that it's centered at 0. See if this will actually let me write on here. Okay, so that means it's centered at 0. For the degree n equals 5, for the function sine x, we are going to use a 5th degree Taylor polynomial to approximate sine of 0.1. That 0.1 is my x value. What we need to do is start taking the derivative of sine. We're going to do a lot of prep work so that setting up the polynomial is easy. So what I would suggest doing, if you see n equals 5, or if you see this notation, both of these are telling me the same thing, telling me that I need 5 derivatives. So take the derivative 5 times. So we're going to start with our original f of x, which is sine, and I need to take the derivative 5 times. So f prime. After 3, you can just write 4. So just keep taking the derivative. Derivative of sine is cosine. Derivative of cosine, negative sine, negative cosine, back to sine, and then back to cosine. So if it says something about a 5th degree, whatever degree polynomial it says that you're going to have, you're going to calculate that derivative that many times, which means in your polynomial, you won't have 5 pieces, you'll actually have 6, unless something like zeroed out at some point, and that does happen. It's going to happen here. The next thing we need to do, because it's centered at 0, in your formula, we need the derivative, but we also need to know the value at that center value. So we're going to plug in 0 for each one of these. The term Maclaurin is what gives that away. Yep, so if it says Taylor polynomial, chances are it'll straight up say like it's centered at a certain value. If it says Maclaurin, then that's automatically 0. So we're just going to plug in 0 for all of these values, for all of these functions. Shouldn't be too bad because the sine and cosine should be bouncing from 0 to 1, and it might have some negative ones. So a little bit of unit circle stuff. 0 is over here. My coordinate point is 1, 0. Cosine is 1. Sine is 0. So for all of my signs, regardless of whether it's positive or negative, they should all be 0s. And then my cosine should be bouncing from 1 to negative 1. So even though this is a fifth degree polynomial, because some of these pieces are zeroing out, our polynomial won't have that many pieces. It'll probably have about half, okay? But I'm going to write out the whole formula. I'm going to do the whole thing, and then we'll simplify it. At some point, you could definitely start, there are some shortcuts that you could take when you're writing these, but when you're first starting, I would highly suggest doing all of the derivatives, figuring out all the values, do all this behind the scenes work, then we can plug it into the formula. Is there anything so far that I've done that you have questions about? Good at that? Okay. All right, so we're going to create that polynomial using the formula. So the formula is where we take the f of 0 value, or whatever it is, so we're going to do f of 0. Then I'm going to add the first derivative times that x minus the c piece. But my c is 0, so I'm not going to write that. Okay? If you want to use it, you certainly can. All over 1 factorial, or just 1, which I don't need to write once again. Then I'm going to do the second derivative times my p squared over 2 factorial. Then I do the third derivative times the p's cubed over 3 factorial.
So if some of these are zeroing out, like they're going to be crossing the...
Yeah.
Okay.
So then I'm going to do the fourth derivative times x to the fourth over 4 factorial. And I'm running out of room, but I'll just put it right below this, plus the fifth derivative times x to the fifth over 5 factorial. If it is a free response question, as I've said before, you don't have to simplify, so you could just leave your factorials. If you even have like a fraction that you want to leave unsimplified, that's fine. If you're doing a free response question, of course, that might be how they kind of take it up a notch, where you actually have to figure out which one is the same as what you have. And also there are questions where you are backwards. Sometimes they'll give you the polynomial, and you have to figure out what this number would have been. Okay, and we'll do some of that either maybe today or next time. All right, so we're just going to replace all of those values with what we already found. So f of 0 is 0, so that's going to cancel out. Also, my second derivative and my fourth derivative. So I'm going to have 3 pieces in my polynomial. My f prime of 0 was 1, so I get x, plus the third derivative was negative 1. So I guess I could actually just scrap this negative, or the positive and put a negative. Either way, it doesn't matter. And then x squared over, or not x squared, x cubed over 3 factorial plus x to the 5th over 5 factorial. If you do all of this work, taking the derivative and plugging in, once you do the formula, that's like the easy part. What do you think? You will never actually have to derive this polynomial again. This is one of the ones that the AP test recommends that you memorize. So one thing with sine, we can see that all the even pieces are canceling out. So with sine, start to think of odd. We got first, third, fifth, and also the signs alternating positive, negative, positive. You don't have to worry about memorizing the factorials because the factorial is going to match whatever the exponent is. Okay. Now, if you want to actually find the value of sine of 0.1, what do we do with 0.1? plug it in for x. Okay, so plug in 0.1 everywhere you see an x. This would obviously, like, if the AP test wanted you to like actually simplify that, it would have to be a calculator active question, okay? You can just leave it like that. If you do type it all in, I can tell you that you would get approximately 0.0998, if you want to know that.
Is that radians or degrees?
0.0998. Radians. Anytime we are doing something in calculus with sine or cosine or any trig function, radians. That's a good question. Yeah, so one thing, like when you're taking that AP test, put your calculator, I would say for the most stuff, because of trig, you're gonna need radian mode. Unless you start dealing with polar or parametric, then you might play with it. But I can't think of anything where you would want degrees. Okay? Good question. All right. What do you think? Not bad if you can take a derivative, right? So we're going to do one more of those. And then I'm going to show you a couple of things where you can kind of work backwards. And that's where we'll stop for today. Okay? So for number 2, we are finding a Taylor polynomial of the 6th degree, which means that you need to take the derivative how many times? 6, okay? You're doing that for ln of x. So go ahead and take the derivative 6 times. This part's very tedious and you want to be really careful, but like if you take the time and you do correct work here, it will make everything else so much easier. Some people do the whole thing in their head at once, like they'll find each piece of the polynomial and do that derivative as they go. I don't recommend that, but certainly if you want to do that, that's up to you. So I've got those 6 derivatives up here, and then just plug in 1. And it will be much easier to just plug in 1 once you have that positive exponent, because that's going to be the denominator. It's going to kind of just disappear. So plugging in 1's not bad because it just makes that denominator kind of disappears. You're really just looking at the numerators. So I'm just grabbing, you do need to know that ln of 1 is 0, but when you plug in 1 here, 1, then we're getting a negative 1. From there, I'm just grabbing the numerators, 2, negative 624, negative 120.
Why are we just grabbing?
Because when I plug in 1 to the 6 is just 1, and so it just kind of irrelevant. It's not doing a whole lot. Like the whole polynomial?
Yeah, like once we have it written out and give
Yeah, it just depends. Like if it's a calculator active question, you know, the AP test, there's multiple and free response questions that are calculator active and that are not. If it's calculator active, it's very well that they might have you simplify it a little bit further, unless it's something like an easy fraction to simplify. But if it's a free response, the good thing is that you can leave it completely unsimplified. Just set up the polynomial. You're actually better off to do that, because if you try to reduce a fraction and you reduce it wrong, then you're going to lose points. So when I'm grading your stuff, I'm fine with that. Any questions on the derivative or plugging in? That's the easy part, but it's also the part that it's tedious. So if you do mess up something there, it's going, it's obviously going to create a problem with the rest of your polynomial. But if it's a multiple choice question and you do just mess up one part, you might still be able to figure out which answer is right, okay? So that's the good thing about some of those multiple choice questions. All right, setting up the polynomial, we've got that formula, but honestly, you really don't need it. You always just start with your first piece, so your f of 1. Then I'm going to add on my first derivative, multiply it by x minus the c value. First derivative to the first power over 1. Then I'm going to do the second derivative, because this one's centered at 1. So with the last one, it said McLaurin, so that automatically meant it was centered at 0. And you could have written x minus 0 if that makes you feel a little bit better, but I just put x. Did you just leave off the minus 1 and do x? Yeah. So if it says McLaurin, that's an x minus 0, so the 0 is going to kind of disappear. But if it says it's centered at a certain value, we have to put x minus that number. Yeah, these numbers should always match. Whatever your value is here should be here. And with the last one, because it was 0, when I'm plugging in 0, I just didn't even bother to put it. But if it makes you feel a little bit better, like when you're doing your formula for consistency, you can totally write it out. Especially until you get, this is brand new, you've never seen this before. So it'll take some time to get used to it. We've got the second derivative squared over 2 factorial. Once you get in the swing of that pattern, you just keep 3, 3, 3, 4, 4, 4. 3. The other thing is these do take up a lot of room. So I'm going to add on my next 2 pieces down here. So I should have 6 derivatives, which means I should have a total of 7 pieces. That's something that'll throw off a lot of people when they see that says something about a 6-degree polynomial. They think, oh, it should have 6 pieces. No, it's actually going to have one more than that. Okay. However, we do have one piece that cancels out, because our f of 1 is 0. And now everything else that I need to do is I just need to replace these values that we found into the formula. So I'm going to actually find my Taylor polynomial by replacing these. And I'm just going to be lazy and erase. And that's something that you might do too, especially if you're working with a whiteboard. I feel like I'm going to erase and have to go back and rewrite some stuff. Alright, so it was 1 to the first. What number's there? -1. If you want, if you do all of this work that we did, all this prep work, and you want to jump straight to this, like skip writing out the f prime of 1 and f prime of 2, that's fine. I think that will happen at some point. I'm just really working out every little step because, like I said, this is brand new. So, like, you might have to do this for a little while before you get comfortable, like, skipping some of those steps. So that is what the polynomial looks like. So if you're asked, this is a great like free response multiple part question because you could be given a series in the problem and you're asked to calculate the Taylor polynomial, then you're asked to find an approximation. So it's a great thing, like you can do so many different things with this one polynomial. You can actually even take these polynomials and create a series from it. Like, that's what we're doing. It's like we're adding together a bunch of pieces, okay? If you wanted to know the approximation of ln of 1.1, we would just plug in 1.1 everywhere that we see x, okay? So you could replace all of these parentheses with 0.1s, right? Because 1.1 minus 1. So I would have 0.1 minus 0.1 squared over 2. This would be a totally acceptable answer on the free response, the way I'm writing this. Just saying 0.1 squared over 2 factorial. 0.1 cubed over 3 factorial. Oh, we are. So like the x value is 1.1. And so when you plug in 1.1 and subtract 1, you get 0.1. I think probably what's confusing is the last one I just had 0.1. Is that what you were thinking? Yeah. Like there's a lot of moving pieces in this. Like I don't think any one part of it is like hard. Like I said, it's tedious. I'm running out of room, but you know what goes there. That would be the approximation, and that's an acceptable answer. You don't actually, unless it's a calculator question, no one's going to expect you to be able to do that without a calculator. It's just, I know how y'all feel about college boards sometimes, but like, they're not that mean, okay? That would be awful.
How would you even go a lot of multiple?
Yeah, you're squaring and cubing 0.1, and 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4.
It's not that bad.
No,
It takes so long to do.
But the thing, and then there probably is some reducing that you can do there. No one's going to expect you to do that. Like if